Hello everybody, my name is eMoney SD. Welcome back to my YouTube channel, and today we're going to go ahead and cover chapter 6 of David Klein's Organic Chemistry textbook. Now, chapter 6 is all about chemical reactivity and mechanisms. This chapter actually covers a lot of really important topics, and in this first few sessions we're going to cover topics specifically about thermodynamics and kinetics, and we're going to learn to describe the favorability and rate of reactions. We will start with thermodynamics. Here we're going to answer questions like, well, how do you know if a reaction will be spontaneous or not? How much energy is available to do work? The answers to these questions lies in this term called Gibbs free energy, and we're going to use this formula to gauge the spontaneity of a reaction. Two terms that are a part of this equation that we're going to discuss in detail is enthalpy and entropy. We will look into both with great detail. Gibbs free energy is the most important equation for understanding a reaction's favorability / spontaneity. When we use the term spontaneous, though, we are talking about whether a reaction occurs or not, and not about the speed. When we talk about the speed, we're going to be talking about kinetics, and that's something we're going to discuss in the next section, actually. So, anyway, in order for a process to be spontaneous, in order for a reaction to proceed, the change in Gibbs free energy has to actually be negative. In order to understand this, we're going to have to begin by exploring each term in the equation. All right, delta H in our Gibbs free equation is enthalpy. It's the enthalpy term. Enthalpy is the sum of bond dissociation energies for a reaction. When we have negative values, we say the reaction is exothermic. If we have positive values, we say the reaction is endothermic. Delta S, the term delta S in our Gibbs free energy stands for entropy. It's the entropy term. And entropy is the tendency of a system to take its most probable form. And then T, of course, is temperature. Now, these three terms are going to help us understand what is happening when we look at a reaction where reactants are being converted into products. What's happening here? Are bonds breaking? Are bonds forming? How many moles are being formed or converted? How many species are we dealing with? What is the temperature change? All of these things are things we ask or want to figure out when we are looking at a reaction. And in order to do this, let's really start by exploring enthalpy a little more first. Enthalpy is a property of a thermodynamic system, and it is a measure of heat in the system. So you can think of it, delta H, enthalpy, as a heat term. In other words, enthalpy is used to measure the exchange of energy. Kinetic energy specifically, the kind that leads to bond formation and bond breaking, for example. Now, bond dissociation energies describe the strength of chemical bonds. It can more specifically be defined as the standard enthalpy change when, say, AB, and let's write this down, when AB is cleaved homolytically to give fragments A and B. So if A and B were to be broken homolytically, so each atom in this molecule, when we break their bond, they each get one of the electrons that's being shared. So bond dissociation energies describe the strength of chemical bonds, and it is more specifically defined, right, as the standard enthalpy change when this occurs. Now, these can be determined experimentally. These values can be determined experimentally for bonds, and you can see these values for common bonds in this table right here. This is in the David Klein textbook. All right, and it's very useful, and you're going to be using this table to do practice problems in regards to the bond dissociation energy of a whole reaction. Now, in addition, negative values of enthalpy, all right, are called exothermic reactions. What is occurring here, in other words, is bond formation. Positive values for enthalpy is an endothermic reaction. This occurs with bond breaking. Awesome. Note that the total change of an enthalpy for any reaction is referred to as the heat of reaction, and it's a measure of the energy exchanged between system and surrounding. And just one more time, because this is an important point, when enthalpy has a negative value, that is referred to as an exothermic reaction. This signals the transfer of energy from system to surrounding. All right, an example, again, bond formation. All right, now when enthalpy has a positive value, that is referred to as endothermic reaction, and this signals a transfer of energy actually from surrounding to system. And a good example of this, like we just said, bond breaking. All right, so these kinds of notes right here, very important. All right, highlight, color code, whatever. Just remember this. Now let's calculate the heat of a reaction for an example problem, just so we can see how we can use this table of experimentally obtained bond dissociation energies of common bonds to go ahead and figure out the heat of a reaction. All right, so let's start here. Let's do this practice problem right here. All right, when we're trying to find the heat of a reaction, we want to start off by writing and making notes of a couple things. What bonds are being broken? And what bonds are being formed? That way, we can go ahead and look at our table to get the values for those for the bonds that are broken and the bonds that are formed, and then calculate the heat of the reaction. So, looking at this reaction, all right, we have this molecule that we start off with, all right, and it is changed as the reaction proceeds. This bromine group actually breaks off, all right, because it is in the reactant side, in the product side, it is no longer a bromine but an alcohol group. So one of the bonds that is broken is this whole molecule, specifically the bromine group is broken off of this tert-butyl group right here. All right, so we write that down. This is being broken. Now, if you look at your table, all right, the value for that bond is going to be, let me see if I could find it on here. Where is it? It should be 272 right here. Look at that. All right. So we're going to go ahead and we're going to write that 272 kilojoules per mole. Now, what else is broken is this water molecule right here. We lose a hydrogen. We lose an alcohol group. What's completely lost is this whole alcohol group, and it's replaced by a bromine. Okay, so the alcohol group in this water, the OH in water, is broken off. Now, the value for this is 498 kilojoules per mole. All right, so these are the bonds that are broken. Now, what bonds are being formed? Obviously, these two products are being formed. So we're going to go ahead and we're going to write that. So CH3C now with an OH. All right, and then we form hydrogen bromide. Now, the values for these are 381 kilojoule per mole and 368 kilojoule per mole. Now, we have all the values. How do we figure out the heat of the reaction? Well, the equation for this, and I'm going to write it in a different color, is bonds broken minus bonds formed. And that will give you your heat of reaction. Awesome. So we're going to go ahead. We're going to do, that means 272 plus 498, right? Because that's the total for bonds broken. Minus the bonds formed, that's 381 plus 368, right? Bonds formed total. And we're going to go ahead and we're going to subtract these two. What we get is 21 kilojoules per mole. All right, so that is a positive value for the heat of reaction. That means this reaction is actually endothermic. That means the energy is being moved from surroundings to this system. And so the system is gaining energy. Sorry for my awful handwriting. All right, so that is how you determine the heat of a reaction for a reaction. You figure out the bonds that are broken, you figure out the bonds that are formed, and then the formula you use to get the heat of the reaction is bonds broken minus bonds formed. If you get a positive value, guess what? Your reaction is endothermic, and the energy is being moved from your surrounding into your system. If it is negative, then it is exothermic, and your system is moving energy into the surroundings. Fantastic. I hope that makes sense. Let's go ahead and move into talking about entropy now. All right. Enthalpy, first of all, is not enough to determine whether a reaction is favorable or spontaneous or not. So then we have to introduce entropy. The level of order it requires is needed too. So entropy is defined as the measure of molecular disorderness. This term or value is actually statistical in nature, but no math here. Instead, we're going to focus on chemical patterns that are going to help us determine if a reaction has positive entropy or negative entropy. Positive entropy means it means favored, and negative entropy means the reaction's unfavored. The three patterns are increasing the number of molecules. So if you start off with one molecule and you end up with two, or if you end up with 1 mole and if you start with 1 mole and end up with 2, right, you're increasing the number of molecules. All right, if this happens, then your reaction has positive entropy. All right, if it's the other way, if you have 2 molecules and you go to 1 molecule, that reaction has a negative entropy. Okay, now the next pattern is phase transition. Okay, if you go from solid to liquid, my pen does not want to work. If you move from solid to liquid, all right, if you move from solid to liquid, your reaction has positive entropy. If you move from liquid to gas, your reaction also has positive entropy. So going down this. If you go from solid to gas is also positive entropy. All right, but if you're going backwards on any of these, and let me do that in a different color, blue. If you're going from liquid to solid, your reactants are in liquid form and your products are solid, then that is negative entropy. And same for all of these. All right, so phase transition is another way to determine, all right, if your reaction has positive or negative entropy. And this has to do with going from highly ordered to less ordered structures. Your solid structures are more ordered, and if you're going into less ordered structures, then you're increasing in entropy. All right, the third pattern is your molecular freedom of motion. So if you start with a cyclic molecule and you end up with an acyclic molecule, your reaction has positive entropy. All right, if you go from acyclic to cyclic, then your reaction has a negative entropy. And the best way to really understand this is actually just to do a practice problem. So we're going to look at this practice problem. It says, which of the following reactions, A, B, C, D, or E, has a positive sign of entropy? All right, so let's look at our first molecule. Let's look at our first reaction. All right, we have a cyclic molecule. All right, and it's going to a cyclic molecule. We start off with 1 mole to 1 mole, and we don't know if it's a solid or liquid or gas or whatever, so we can't base it off of that. There's nothing really that's happening here that we can tell in regards to entropy. Well, what about the second one, B? All right, we start off with 1 molecule, we end up with 2. We've increased the number of molecules. This reaction has a positive entropy, so one of the answers is B. All right, C, we're going from acyclic, right? This is not a ring structure, into a ring structure. All right, this is negative entropy. It's only positive if you go from cyclic to acyclic because you're increasing your freedom in motion. All right, D, you're starting off with 2 molecules, you're going to 1. That is negative entropy. All right, and then this one is simply a movement of charge. nothing here is occurring in regards to going from cyclic to acyclic, and you have 2 molecules to start off with and 2 to end, so there's nothing here that's happening that's that there's a positive sign of entropy that we know of based off of our 3 patterns. So the reaction that has a positive sign of entropy is gonna be B. Awesome. So now what we really want to talk about is a little bit on where we get this Gibbs free energy formula. So just to reiterate, our Gibbs free energy formula looks like this. And we've covered our enthalpy term, we've covered our entropy term, what those are, how to figure them out, and we know T is temperature. But really, where does this formula come from, right? Because that's important to understand. So let's start by looking at total entropy and defining total entropy, right? Okay, we're going to start off by talking about how to calculate total entropy. So total entropy, well, it is an addition of the entropy of your surroundings plus the entropy of your system. Now, this is a term we can obtain, all right? But what is this? What is the entropy of our surroundings? Well, there's actually a definition of this, all right? The entropy of our surroundings under constant pressure and temperature is actually defined as the negative enthalpy of the system over temperature. So then if we take this, right, and we plug it back in here in our total entropy term, all right, what we get is something that looks like this. Total entropy is equal to minus enthalpy change of the system over temperature plus the entropy of your system. Well, if we multiply both sides, right? If we multiply both sides by temperature, actually negative temperature, what we get is negative temperature multiplied by the total entropy equals delta H of the system, right? Because this cancels out with this, plus, actually not plus, minus temperature and the entropy of the system. We redefine this term. This term is redefined as delta G, or our Gibbs free energy term. And what we see here is that delta G is nothing more than a repackaged way of expressing total entropy. We said that delta G has to be negative for the reaction to be spontaneous. All right, and we have figured out through some quick math, all right, that delta G is nothing more than a repackaged way of expressing total entropy. And that's a pretty cool conclusion. Now, again, for a reaction to be spontaneous, for a reaction to move from reactants to products, delta G has to be negative for the reaction to be spontaneous. This table does a really good job demonstrating the signs that you need for enthalpy and entropy, as well as the needed temperature to get a negative delta G. All right, so if you have a positive enthalpy and a negative entropy, all right, if your entropy term is negative and you're multiplying it by a negative temperature, that overall term is positive, all right, and your delta G is going to be positive, and that's not spontaneous. Now, if your enthalpy is negative, your entropy is positive. If it's positive, then the whole term right here is negative, and your delta G will also be negative, and so a reaction is spontaneous. Now, in any other case, for a mix and match of enthalpy and entropy, it really depends on the temperature, whether it needs to be low or high, to determine whether the reaction is going to be spontaneous or not spontaneous. Remember, just really quickly so we could view a quick chart, all right, of delta G versus your reaction coordinates, all right? If the difference in delta G is negative, then your reaction is said to be called exergonic. And if the difference is positive, if your delta G is positive, then it's called endergonic, and those reactions are not spontaneous. Now, one more note on Gibbs free energy before we end the session. Remember when we did acid-base equilibria, right? We talked about whether our reaction would favor from reactants to products, if that's where the reaction lied, or if it lied from products to reactants. Now, KEQ is a term that describes the exact position of equilibrium for any reaction. So if your KEQ value is greater than 1, then your products are favored. If it's less than 1, then it favors reactants. And if it's equal to 1, then your reaction's already in equilibrium. Well, something that's really cool is that there's a relationship between equilibrium constant and Gibbs free energy, and this equation demonstrates that relationship. Now, something really cool, if your delta G is positive, all right, your reactants are favored. And that makes sense, right? Because a negative delta G means that the reaction is spontaneous and will move from reactants to products. If it's positive, then your reaction is not moving forward from reactants to products. Your reactants are obviously favored. And like we said, if it's negative, then your products are favored. So if we look at this example problem here, if delta G is a positive value, where does your reaction lie? Obviously, it lies in your reactants. And if our KEQ is 0.5, well, we said if KEQ is less than 1, then your reaction favors reactants. I hope that this helps introduce these important terms and topics for thermodynamics. If you have any questions, let me know. Next session, we'll dive into kinetics. Happy studying and have a great day.